topic we'll be discussing in this lecture is radio interface. So radio interface is represented using UM. So it is represented using the notation UM. GSM implements SDMA, that is space division multiplexing, using cells with BTS and assigns MS to a BTS. That is, the mobile stations are assigned to base transmitting stations. Okay, base transceiver station. And frequency division and FDD, frequency division duplexing, is used to separate downlink and uplink. Frequency division multiplexing is used to separate downlink and uplink communication. Media access can happen, that is, the wireless medium can be accessed either through TDMA or it can be done through a combination of TDMA and FDMA. So if we see GSM 900, GSM 900 has 124 channels, and each channel width is 200 kilohertz, and it is used for basically FDMA, frequency division multiple access. Out of the 124 channels, 2 channels are not used for technical reasons. Channel 1 and channel 124 were not used. Okay, so here this is not 2, it is channel 124. Out of these two channels were not used. These are channel 1 and channel 124. The first channel and the last channel were not used. And 32 channels were reserved for organizational data, and remaining 90 channels are used for customers. So each BTS, that is base transceiver station, manages a single channel for organizational data and up to 10 channels for user data. Each BTS manages single channel for organizational data and up to 10 channels for user data. Similarly, the GSM 1800 and 1900 also works in the similar fashion. So, there are totally 248 channels, because there is 124 in uplink and 124 in downlink. So there are totally 248 channels, and each of these 248 channels are again separated in time. They are separated in time through a GSM TDMA frame, because there should be a God space, right? So because of that, they are separated in time. And each of the 200 kilohertz carrier is subdivided into frames that repeat continuously. Each of the 200 kilohertz channel is subdivided into several frames which will repeat continuously, and the duration of each frame is 4.615 millisecond. Duration of each frame is 4.615 millisecond, and each frame is again subdivided into 8 GSM time slots. Each frame is subdivided into 8 GSM time slots, where each slot represents a physical time division multiplexing channel, and it lasts for 577 microseconds. Okay. Each frame is divided into 8 GSM time slots, where each time slots last for 577 microseconds. So this is how the radio interface is uh, uh, structured. Okay, so this is what we have discussed so far. That is represented in this diagram. So here we can see that each frame each frame so this is one frame, okay, and each frame is divided into 8 slots. The total duration of the frame is 4.615 microsecond. So if you take one slot, the duration of one slot is 577 microsecond. Okay. The duration of the frame is 4.615 millisecond, not microsecond. Duration of the frame is one entire GSM TDMA frame is 4.615 millisecond, and each frame contains 8 slots. And if you take each slot uh, will last for 577 microseconds. Data is transmitted in small portions, which is called as burst. Data is transmitted in small portion, which is called as burst. So this diagram, what it shows in the sense, it shows a normal burst. It shows a normal burst. So in a normal burst, the burst is only in the normal burst. The actual burst, even though each slot can maximum have 577 microseconds, in a normal burst, the burst is the burst length is only 546.5 microseconds. Okay, because there are some God spaces, because there is a God space in the beginning, and also there is a God space at the end. Because of that, the 577 microsecond slot was reduced to 546.5 microseconds long. Okay, and it contains totally 148 bits. It contains 148 bits. Okay, so if you add up all these bits, you will get 148. So 57 bits for user data. There is another 57 bits for user data, so which is 114. There is 126 bits for uh, what you call training. So 114 plus 26 is 140. Okay, 140 plus 3, 143, 146, 147, and 148. So it contains totally 148 bits. Okay, the remaining 30.5 microseconds, because for 546.5 microseconds only, that there is the actual burst. The remaining 30.5 microseconds, if you subtract 577 from 546.5, what you get is remaining 30.5 microseconds. That is used as a God space. Okay, to avoid overlapping with the other burst. To avoid overlapping with the other burst. So, so this is the structure of the radio interface. And each radio carrier transmit approximately 270 kilobits per second. Each radio carrier transmit approximately 270 kilobits per second over the radio interface. Okay, fine. So we'll come to this diagram later. Then we'll discuss this. So, so, so in the normal burst, so we are discussing about the normal burst, which is represented in this particular diagram. So the normal burst, we can see that uh, the tails are set to 0, and it can be used to enhance the receiver performance. So there are tail. So there is something called tail. So this which occupies 3 bits. There is a tail at the beginning, and also there is a tail at the end. These tails are normally set to 0, and it can be used to enhance the receiver performance. Okay, and there is a training sequence in the middle. Here there is a training sequence which occupies 26 bits. So the purpose of this training sequence is to adopt the parameters of the receiver to the current path propagation characteristics, and to select the strongest signal in case of multi-path propagation. So already we have discussed that wireless channel there are a lot of chances for multi-path propagation. So when the signal is when the signal is going through multi-path propagation, the receiver will receive the signal from different what you call different path. So out of that, the receiver should identify which is the best path, and that path only the receiver should take. So that was done by the training sequence. That was done by the training sequence. Okay, training sequence ensure that the receiver adopt to the correct parameters based on path propagation characteristics, and it selects the strongest signal in case of multi-path propagation. Similarly, there are yes bits. There are yes. Okay. Yeah, basically, this yes is a flag. A flag yes indicates whether the data field contains user or network control data. Okay. So there is a flag yes. Here is a flag yes, and here is another flag yes, which is of 1 bit length. So there are two user bits of 57 bits. So this yes bit basically says whether the data bits, whether the user data bits, which it contains what, whether it contains user data or network control data. That is represented using the yes bit. And normal burst defines four more burst for data transmission. Normal burst defines four more bursts for data transmission. These are, the first is frequency correction burst. The first is called as frequency correction burst, which allows the MS to correct the local oscillator to avoid interference with the neighboring channels. So this frequency correction burst is basically to adjust the mobile station to the current frequency so that it can avoid interference from the neighboring channel. Okay. So this is the first burst, and the another burst is synchronization based burst. Synchronization burst, it provides an extended training sequence to synchronize the MS with the BTS. It provides an extended training sequence to synchronize the mobile station with the BTS based transceiver system. And also there is a dummy burst. It is used if no data is available for a slot. Okay. So the normal burst defines these these burst also. Okay. And also there is an access burst. There is something called access burst. It is used for initial connection setup. Under normal burst, we have all these four bursts. Okay. Okay. Frequency correction burst, which helps the MS to tune itself to synchronize with the local oscillator, and synchronization burst, which helps the MS to synchronize with the BTS, access burst for initial connection setup, and dummy burst is used if no data is available for a particular slot. So, so there are two factors allow for the use of simple transmitter hardware. The slots for the uplink and downlink of a physical time division multiplexing channel are separated in frequency. So for uplink, the frequency 445 megahertz for GSM 900, 95 megahertz for GSM 1800. Okay. On the other hand, TDMA frames are shifted in time for 3 slots. TDMA frames are shifted in time by 3 slots. So that is, if the BTS send a data at time 0 in slot 1 on the downlink, the MS access, there is a mobile station access slot 1 on the uplink at time t plus 3.577 microseconds. Okay. So the MS does not need a full duplex transmitter, which the mobile station does not need a full duplex transmitter. A simplex half duplex transmitter switching between receiving and sending is enough. Full duplex means both the device can communicate, send and receive data at the same time. Half duplex means if one is sending, then the other should listen. Okay. So the next thing that we'll be discussing is logical channels and frame hierarchy. So if you look at the logical channels and frame hierarchy, uh, this pattern is followed. Say, let us assume, let us think of a logical channel C1. Let us think of a logical channel C1 that takes up every fourth slot. Let us think of a logical channel C1 that takes up every fourth slot, And also let us think of another logical channel C2 that uses every other slot. There are two logical channels C1 and C2. C1 will take every fourth slot and C2 will take every other slot. Okay. So this can be represented by using this pattern C1, C2, X, C2, C1, C2, X, C2, C1. How in the sense? So we said that C1 will take every fourth slot. So let us assume this is fourth slot. Just assume this is the fourth slot. Okay. And C2 will take every other slot. So the previous slot is C1 means the next slot should be surely C2 because C2 will take every other slot. And the next slot will not be C1 and also it will not be C1, C2 because C1 will be every fourth slot. So currently it is fourth. Previously it was fourth means then eighth slot will be the next C1. Okay, so the next slot will not be C2 also because C2 will be every other slot. So the next slot is some X. We don't know what is that. And after X surely there will be C2 because it will not be C1 because C1 will be fourth slot, every fourth slot. Okay, the next slot will be C1 because from here if you take 4 plus 4 8, so this is 5, this is 6, this is 7 8, so every fourth slot will be C1. Next slot will be C2. The next slot we don't know, so it is X. Okay, again next slot is C2, again next is C1 because if this is fourth slot the if this is then this is 9 10 11 and this is 12th slot. This is the next fourth slot. So this is how the pattern follows. Okay, so that is every fourth slot will be occupied by C1 and every other slot will be occupied by C2. Okay, the X indicates that the physical channel still has some capacity left for other channels. Okay, right. So GSM specifies two basic groups of logical channels. These are traffic channels and control channels. So first let us try to understand the traffic channels. So the traffic channels is represented as TCH. Traffic channel is represented as TCH. So GSM uses a TCH to transmit user data. User data like voice or fax messages, whatever it may be. Okay. So there are two basic categories of traffic channels, that is TCH. TCH stands for traffic channel. There are two basic categories of TCH were defined. One is full rate TCH, which is called as TCH/F. And the other one is half rate TCH, which is also called as TCH/H. TCH, the full rate TCH, the full rate traffic channel has data rate of 22.8 kilobits per second. The full rate TCH has data rate of 22.8 kilobits per second, and the half rate data traffic channel has a data rate of 11.4 kilobits per second. Okay. With voice codecs available with the GSM standardization, 13 kilobits per second were required. Okay. Whereas the remaining capacity of TC of traffic channel 22.8 kilobits was used for error correction. Okay. So with voice codecs, with the support of voice codecs, so the traffic channel, the full rate traffic channel, it provides a data rate of 22.8 kilobits per second. Okay, but with voice codecs, by adding coder by adding some coding and decoding techniques, 13 kilobits was required to transmit data. So the remaining capacity, because TCHF traffic channel with full rate, it supports up to 22.8 kilobits. So in this we are using only 13 kilobits for data transmission. So there are some remaining around 10 bits or 9.8 kilobits per second. Okay, so that can be used for error correction. Remaining whatever the data rate is available, which is unused because only 13 kilobits per second were used with the inclusion of codecs. The remaining thing can be used for error correction. Okay. So the improved codecs that is the latest development in codecs, allows for better voice coding and can use a TC TCH/H instead of TCH/F. So we have special codecs. So with that, instead of going for a traffic channel with full rate, even we can go for traffic channel with half rate. Okay. So using these half rate traffic channels doubles the capacity of GSM system for voice transmission. Okay. Because of the introduction of codecs, you need not even use a full rate traffic channel. You can even use a half rate traffic channel. So that doubles the capacity of the GSM for voice transmission. Okay. But what happens in the sense, the speech quality decreases with the use of half rate TCH. Okay. But the speech quality decreases with the use of half rate TCH, and that is the reason why most of the service providers try to avoid the usage of half rate TCH. Okay. Because of this reason, most of the service providers, they try to avoid using half rate TCH. So the standard codecs for voice for full rate TCH, it operates at 13 kilobits per second, and for half rate traffic channels, it operates at 5.6 kilobits per second. So obviously 5.6 means less, so its quality decreases. Okay, a newer codec, which is an enhanced full rate codec, it provides better voice quality than than full rate, as long as the transmission error is low. Okay, there is an enhanced full rate coder which even provides better quality than than full rate TCH until the error rate is low. Okay, so the generated data is only 12.2 kilobits per second with the new codec. The new codec which automatically choose the best mode of operation depending on the error rate. Okay. So depending on the error rate, it will choose what operation, what mode it should work. Okay. An additional increase in the voice quality is provided by something called as tandem free operation. So radio interface also supports something called as tandem free operation. Through that, additional improvement in voice quality is provided. Okay. So this is how the traffic channels radio interface works. So what we have discussed in the sense, there are two types of traffic channels. One is full rate traffic channel, the other one is half rate traffic channel. The normal data rate of full rate traffic channel is 22.8 kilobits per second, whereas for half rate data channel is 11.4 kilobits per second. But with the introduction of voice codecs, data can be transmitted effectively at 13 kilobits per second. So the remaining bits were used for error correction. Okay. So GSM, instead of using full rate traffic channels, it can also use half rate traffic channel. By using half rate traffic channels, the GSM's capacity can be doubled. But most of the service providers, they don't prefer using half rate traffic channels because it reduces the voice quality. There is a new codec called enhanced full rate codec. It provides better voice quality than the full rate traffic channel, as long as the error rate is low. So and there is something called a tandem free operation, which can further increase the quality of the voice. Okay. So data transmission in GSM is possible at many different rates. Okay, example, we have traffic channels at full rate, which is operating at 4.8 kilobits per second, and traffic channel at full rate operating at 9.6 kilobits per second, and the newer specification, traffic channel at full rate operating at 14.4 kilobits per second. Okay, so depending on the different channels, the coding schemes and the error correcting capabilities will differ. For various schemes, for various, depending on the data rate, the coding scheme and the error correction technique used will also differ. So this is about the traffic channel. The next thing we will be discussing is control channel. So many different control channels. Control channels are traffic channels are represented as TCH. Control channels are represented as CCH. Many different control channels are used in GSM. So basically, control channels are used to control the medium access, allocation of traffic channels. Traffic channels were also allocated by control channels or mobility management. Okay. So these are the three prime tasks that were done by control channels. What? It performs control on medium access, allocation of traffic channels, and mobility management. Okay. So three groups of control channels has been defined. Three groups of control channel has been defined. These are broadcast control channel, which is called as BCCH, common control channel, which is called as CCCH, and dedicated control channel, which is called as DCCH. So there are typically three groups of control channel available. These are broadcast control channel, common control channel, and dedicated control channel. So let us try to understand how each of these control channel works. So first let us see about broadcast control channel. Okay. So so with broadcast control channel, BTS use this particular channel. Base transceiver system use this particular channel to signal information to all MS within a cell. So BTS, the one which controls a particular cell. So it uses this particular channel, broadcast control channel, to send some broadcast signal to all the mobile station. Okay. So typically the information transmitted through this channel includes cell identifier. What is the identifier of the cell? Other options within this cell includes frequency hopping. With what frequency hopping pattern the mobile station and the base station should communicate. That information also will be transmitted through broadcast control channel. And frequencies available inside the cell and in the neighboring cell. And at what frequencies are available inside the cell and in the neighboring cell. Okay. So these type of informations were sent by the BTS to the mobile station through this particular channel BCCH. The BTS also sends informations for frequency correction. The BTS sends information for frequency correction via one particular channel called frequency correction channel FCCH. Okay. And information about time synchronization via through a channel called SCH, synchronization channel. So basically, broadcast control channel is used by BTS to, to signal certain information to mobile station within a particular cell. So it sends information like cell identifier, frequency hopping, frequency within the cell and in the neighboring cell, and it uses the channel called frequency correction channel for 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 correcting the frequency, and it uses the channel called synchronization channel for synchronizing the time. Okay, frequency synchronization is done through FCCH, and time synchronization is done through SCH. So this is about broadcast control channel. The next control channel that we'll be discussing is common control channel. So the common control channel, what it does in the sense, it contains all information. Basically, it includes all information. It contains all information regarding connection setup between mobile station and base station. It contains all information regarding to connection setup between mobile station and base station that is exchanged through the common control channel. Okay. For calls forward and MS, the BTS uses the paging channel. Okay, whenever there is a call forward to a mobile station, the BTS uses a channel called as paging channel. Okay, if a mobile station want to set up a call, it uses the random access channel, okay, to send data to the BTS. If any mobile station want to set up a call, it uses the it uses something called as random access channel to send data to the BTS. Okay, so the random access channel is represented as RACH, and this RACH implements multiple access. This RACH implements multiple access using slotted aloha. We have discussed slotted aloha previously, where each user can start sending data at the beginning of the slot. So here collision may occur with other MS in the GSM. Okay. So the BTS uses the access grant channel to signal an MS that it can use a TCH or SDCH for further connection setup. Okay. So when more than one channel try to make a call connection at the same time, then there may be collision. Okay. So BTS uses the access grant channel to inform MS that it can use a TCH or 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 SDCCH. Okay, TCH is traffic control channel, which we already discussed. Okay, and SDCH is standalone dedicated control channel that we'll be discussing the next slide. Okay. So that's it about common control channel. Basically, a common control channel, it contains information regarding connection setup between mobile station and base station. If any mobile station want to set up a call, then it uses a random access channel called as RACH to send data to BTS. And this is done using slotted aloha. Okay, so there may be a collision. And if there is no collision, then BTS uses the access grant channel to inform the MS that it can use the TCH, traffic control channel, or SDCH for further connection setup. Okay, so that is, it informs, it can communicate to the mobile stations through that particular channel, which is AGCH, access grant channel. The next channel that we'll be discussing is uh, dedicated control channel. The previous channels, whatever we have discussed, broadcast control channel, common control channel, all these are unidirectional. Okay, whereas this dedicated control channel is a bidirectional. As long as the mobile station has not established a TCH with BTS, it uses this standalone dedicated control channel. Okay, so in the previous case, we have discussed that if there are more than one users trying to set up the connection at the same time, obviously there will be collision. If there is a collision, then the BTS will use the access grant channel to signal the MS to use TCH or SDCH for further connection setup. Okay. So previously I said, if there is no uh, if the if 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 the connection is successful, no, not like that. If the connection is failed, then the BTS will use the AGCH to signal MS to use the TCH or SDCH for further connection setup. Okay. So as long as the connection is not established, the MS will 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 be, as long as the MS has not established a connection with the traffic channel with BTS, it uses the standalone dedicated control channel. Okay, so SDCCH is standalone dedicated control channel with a low data rate for signaling. So this includes authentication, registration, or other needed things for setting up a TCH, traffic control channel. Okay, each TCH and SDCCH has a slow associated dedicated control channel. Each TCH and SDCCH, that is standalone dedicated control channel, has a slow associated dedicated control channel, which is used to exchange system information. So this slow associated dedicated control channel is used to exchange certain system information such as channel quality, signal power level. Okay, finally, if more signaling information needs to be transmitted, and a TCH already exists, GSM uses a uh, if more signaling information needs to be transmitted and a TCH already exists, then GSM uses something called fast associated dedicated control channel. Okay, so the point is every TCH and SDCH has a slow associated dedicated control channel which is used for exchanging system information such as channel quality and signal power. Okay, if more signaling information has to be transmitted and a TCH already exists means then the GSM will use something called as FACCH, which is fast associated dedicated control channel. Okay, the FACCH uses the time slots which are otherwise used by TCH. So basically, this is used in the case of handover, where BTS and MS have to exchange large amount of data in less time. Okay, so FACCH will be normally used during the time of handover. FACCH will be used during the time of handover when the BTS and MS have to exchange large amount of data in less time. Okay. Okay. So so let us understand with an example how all these things work. Okay. So so the physical channel for data transmission will be something like this. So here is an example where T represents the user traffic in TCH, that is in traffic channel full rate. T represents the user traffic in traffic channel full rate. Okay, T represents the, so here T represents the user traffic in traffic channel at full rate, and S represents the signaling traffic. S represents some signaling information uh, in SACH, that is standalone slow associated dedicated control channel, that is slow associated dedicated control channel. Okay, so there are 12 slots of user data that is followed by a signaling slot. There are 12 slots of user data, and this 12 slots of user data is followed by an signaling data. Okay, and again there are 12 slots of user data. Once again there is another 12 slots of user data, and that is followed by an unused slot. This X or cross, it represents unused slot. Okay, so this pattern will continue. This pattern will continue. So there are 12 slots of user data followed by n signal data, and again there are 12 slots of user data which is followed by an unused data. So this pattern of 26 slot, so totally there are 26 slots. Okay, so this pattern of 26 slot is repeated, uh, it's repeated again and again. Okay, in this case out of 26 we are using only 24 slots. In this case out of 26 we are using only 24 slots for TCH slash F. TCH slash F is a traffic control channel at full rate. Okay, now recall that in the normal burst used for data transmission, in the previous diagram which we have discussed, in the normal burst, okay, in the normal burst, if you go back to the diagram, normal burst, the uh, the number of data bits is totally, if you see, it is the number of the number of bits used for data transmission is 114 bits, because there is one set of 57 bits and another set of 57 bits. It is totally 114 bits, and this 114 bits is repeated for every 4.615 millisecond. Okay, so because this entire duration, because this is one slot. Okay, one slot, in one slot the data transmission is 114 bits. Okay, for one user or one mobile station. Okay, similarly another slot will be used by another mobile station. Okay, So like that, it supports 8 slots in 460 for 4.615 milliseconds. Like that, it will repeat. Like that, it will repeat for every 4.615 millisecond. Okay. So this will result in a data rate of 24.7 kilobits per second. Okay. How we got this 24.7 kilobits per second? So how we got this 24.7 kilobits per second? In the sense, so we know that there are uh, 114 bits. We know that there are 114 bits in in a user data. Okay, there are 114 bits in user data. 114 bits in every slot. In every slot there is 114 bits, and there are 8 slots, and this is going to repeat for every 4.615 milliseconds. And the total data rate. So what will be the total data rate uh, per second? So what will be the total data rate per second? So that is the question. See, there are 8 slots. There are 8 slots. Okay. See, this is slot 1, slot 2, slot 3, slot 4, slot 5, slot 6, slot 7, slot 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 8 slots. In each slot, we are going to transmit 114 bits of data. Okay, and this entire this is one frame. Okay, one frame duration is 4.615 millisecond. 4.615 milliseconds. Okay, so now we want to calculate the data rate per second. Okay, per second for one mobile station. So this 114 milliseconds will be used by one mobile station. Some other mobile station will use some other 114 milliseconds. Okay, so 1 second means what? 1000 milliseconds. So for 1000 milliseconds, uh, how many bits will be transmitted? That is the question. 1000 milliseconds, how many bits will be transmitted? For that, what should we do? We should perform 1000 by 4.615. We should do 1000 by 4.615, which will give the number of frames, that will be transmitted during 1 second. Okay, 1000 millisecond is 1 second into 114 that will give the data rate per second. Okay, so if you calculate that 1000 by, if you calculate that, what we get in the sense, so 1000 divided by 4.615 into 114. So when you do that, what you get is something around 24,702. Okay, so 24,702 bits were transmitted per second. Okay, so if you convert this to kilobits, then it will be 24.7 kilobits per second. It will be 24.7 kilobits per second. Okay, so that is how we got that 24.7 kilobits per second. Okay, I think that is not here where it is. Hmm. So, 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 yeah. So it will repeat, and the data transfer rate is 24.7. Uh, mm, yeah, the data transfer rate will be 24.7 kilobits per second. So again, but this 24.7 kilobits per second is for 26 slots. It's for 26 slots, but we are using only 24 slots. So for 24 slots, what will be the data rate? For that, again, you should do 24 by 26. Sorry, not 24 by 26. You have to do, see, 24. See, this is your data rate. Uh, 24,702 bits per second. 24,702 bits per second. or you can just say 24.7 kilobits per second for 26 slots. Okay, so what will be the case for 24 slots? So what will be the case for 24 slots? Because we are not using two slots. Two slot is not used by TCH, traffic channel. Okay, so that if you calculate, what you get is 24.7 divided by 26 into 24, which is nothing but 22.8 kilobits per second. 22.8 kilobits per second. Okay, so our actual data rate for transmitting this 24 24 slot is 22.8 kilobits per second. Okay, 22.8 kilobits per second. Okay, so this is how this particular concept works. Okay, so if we move further, so this periodic pattern of 26 slots, it repeats. This periodic pattern of 26 slots, it 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 repeats. Okay, the combination of these frames is called as traffic multi-frame. The combination of these frames is called as traffic multi-frame. Mm, and the combination of these frames is called as traffic multi-frames, that is TDMA frames with a duration of 4.615 milliseconds. Okay, to a multi-frame with a duration of 120 milliseconds. Okay, so so the point is the logical combination of 26 frames form a multi-frame. Okay, see, 26 frames form a multi-frame. Okay, where each frame is 26 frames form a multi-frame, and this multi-frame duration is 120 milliseconds. This multi-frame duration is 120 millisecond, where each frame duration is 4.615. Okay, each frame duration is 4.615. So if you multiply 4.615 by 26, okay, see here what we discussed, each frame is 4.615 milliseconds, where each frame contains 8 slots, and the combination of such 26 frames forms one multi-frame. Okay, one multi-frame is equal to 26 frames. One multi-frames is equal to 26 frames. Okay, and the duration of this, and okay, 26 frames, the duration of each frame is 4.615 millisecond. The duration of each frame is 4.615 millisecond. Okay, now we have how many such frames? 26 such frames. So you multiply 4.615 into 26, what you get is nothing but 119.99. 119.99. So that is rounded to 120 milliseconds. 120 milliseconds. Okay, so the point is 26 frames put together forms one multi-frame. Okay, where the size of where the length of each frame is 4.615 milliseconds. So all these 26 frames put together, the duration is 120 milliseconds. Okay, now let us go through that other diagram which we have previously left out. Now you see this particular diagram. So here you can see, yeah, here you can see the see this is one frame. Okay, this is one frame. One frame contains 8 slots, 0 to 7. Okay, and the frame duration is 4.615 milliseconds. 4.615 milliseconds. Okay, so this combination of 26 frames, if you put together 26 such frames, then you get multi-frame. Here you can see multi-frame. Multi-frame contains how many slots? 0 to 25. So totally 26 slots. Okay, whereas each slot of multi-frame is what? Whereas each slot of each slot of multi-frame is nothing but each slot of multi-frame is nothing but one frame. So that is represented by this line. This line should not confuse you. So basically, this is basically overlapping line. Okay, this is basically overlapping line, or I will draw with another color for clarity. Okay, so this each slot of this multi-frame is coming from this frame. Is coming from this frame. Is coming from this frame. Okay, I think it is clear. So each slot of multi-frame is coming from here. So each slot is this, and yeah, so here this is actually an overlapping line, right? Okay, so this is where the each slot is getting. So like that, there are how many frames? There are 26 frames. So 26 frames put together, it form one multi-frames. And the frame duration is 4.615 milliseconds. So the 26 frame duration is 26 into 4.615, which is 120 millisecond. Which is 120 millisecond. Okay, right? I think it is clear. Okay, so this is how the multi-frame is created. Okay, yeah. Now let us continue. Let us continue. We have to keep on move back to this diagram. Let us continue further. Okay, yeah. So this is how the multi-frame is formed. That is 26 frames put together. It forms a multi-frame, and each frame is 4.615 milliseconds. So the multi-frame duration is 120 millisecond. This type of multi-frame is used for TCH, traffic control channels, and SACCH, that is slow associated dedicated control channel, and FACCH, that is fast associated dedicated control channels. Okay, so these logical channels are all associated with user traffic. The multi-frame is called as traffic multi-frame. Multi-frame is otherwise called as traffic multi-frame. Okay, so TDMA frame uh, contains data for other logical channels or combined to a control multi-frame, or combined to a control multi-frame. Okay, control multi-frame, see other signaling informations, all signaling informations of TDMA is put under one particular multi-frame, and that multi-frame is called as control multi-frame. All signaling informations are put together in one particular multi-frame, and that multi-frame is called as control multi-frame. And control multi-frame consists of 51 TDMA frames. And control multi-frame consists of 51 TDMA frames. So again, if we revisit this particular diagram, here you can see, so this is nothing but, sorry, this is nothing but control multi-frame. This is what is called as control multi-frame. So control multi-frame contains 51 frames, normal 51 frames. Okay, so its duration is 235.4 milliseconds, which is nothing but 4.615 into 51. Okay, so when you multiply 4.615 into 51, what you get is 235.4 milliseconds. Okay, so this is control multi-frame. It contains all signaling information. Okay, and how this control multi-frame is formed? This control multi-frame is formed by joining 51 TDMA frames. By joining 51 TDMA frames. Okay, so this particular thing is called as control multi-frames. This is control, okay, multi-frame. I'll call it as MF. Okay, so this is what is control multi-frame, right? So similarly, this logical hierarchy can be extended. 26 multi-frames with 51 frames. 26 multi-frames with 51 frames. Okay, or 51 multi-frames with 26 frames form a super frame. So here you can see these two are super frame. This is also a super frame, and this is also a super frame. But what is the difference? There are two ways in which superframes can be formed. One way is you can combine 51 26 multiframes with 51 frames. You can combine 26 multiframes. You can put together 26 multiframes. Okay, if you put together 26 multiframes, that you can call it as a superframe. Okay, so where is multiframe in our case? This is a multiframe. Okay, this is a multiframe. Uh, so so this particular thing is a multiframe. Okay, so there are two ways of forming superframe: combining 26 multiframes with 51 frames, or 51 multiframes with 26 frames. Okay, so this is formed by combining, this first one is formed by combining 26 uh, multiframes. This first one is formed by combining 26 multiframes with 51 frames. Okay, whereas the second one is formed by combining, the second one is formed by combining uh, 51 multiframes with 26 frames. Okay, see, there are two types of multiframes. What we have discussed is, one is a 26 multiframe, which is a normal multiframe. The other one is a 51 multiframe. This 51 multiframe is also called as control frame, control multiframe. This 51 multiframe is also called as control multiframe. If you combine 26 copies of 51 multiframe, if you combine 26 copies of 51 multiframe, that is can be called as a superframe. Or if you combine 51 copies of 26 multiframe, that can also be called as a superframe. Okay, so I think it is clear. So superframe can be formed in two ways. So this is a 51 multiframe. This is a 51 sequence multiframe. So you collect such 26 frames. You collect such 26 frames, and that will form a superframe. Whereas this is a 26 frame multiframe. You collect such 51 frames. You collect such 51 frames, so that will form a superframe, right? Okay. So this is how superframe is defined. And hyperframe, and next hierarchy is hyperframe. Okay. So 2048 superframes will form a hyperframe. So 2048 superframes will form an hyperframe, and the duration of the hyperframe will be around 3.5 hours. The duration of the hyperframe will be around 3.5 hours. Okay. So this is the overall working concept of radio interface. So we started with the frame. The frame can have 8 slots. The frame can have 8 slots. Okay. Combination of, if you combine 26 frames, that is called as one multiframe. If you combine 51 frame, that is called as one control multiframe. Okay. If you combine 26 if you combine 26 frames of 51 multiframe, that is called as one superframe. Or if you combine 51 frames of 26 multiframe, that can also be called as one superframe. And then if you combine 2047 superframes, that is called as a hyperframe. And the duration of the hyperframe is 3 hours, around 3 hours 50 minutes, 3.5 hours. Okay. So this is about the radio interface, how it works. Okay. So basically we have discussed radio interface under several headings, right? So basically radio interface is referred using UM interface. It is referred using UM interface, and then it and then in GSM, how it in GSM 1800, 900 and 1900, how it is implemented, that we have discussed. And then we have discussed about the TDMA frame, its duration. So its duration is 4.65 milliseconds, and each slot occupies 577 microseconds. And out of that, what are the data bits, what are the signal bits, okay, all these things we have discussed. And finally we have discussed what are the logical channels and frame hierarchy. So fine. Uh, then we have discussed the different types of control channels: broadcast control channel, common control channel, dedicated control channel. And we have taken an example like how the data was transmitted in a combination of 12 slots followed by a signal, and again followed by a 12 slot, 12 data slot, and followed by an empty slot. So this 26 pattern, it keeps repeating. And then we have understood what is a frame, what is a multi-frame, what is a control multi-frame, what is a super frame, and what is a hyperframe. Okay, so let us stop here. Thank you.